Whenever we form a function estimate based on observed measurement data, there are uncertainties associated with this estimate. Some regression techniques, for example Gaussian process regression, are able to directly quantify this uncertainty with each prediction that they make. When using such a data-driven estimate in a dynamic system, this poses the challenge of suitably propagating the uncertainties forward in time to see their effects on the state. Our contribution considers techniques that allow for an accurate propagation of these uncertainties to allow safe and reliable control. Our paper exactly considers such dynamic systems that are described by Gaussian process regression. Now, Gaussian process regression is a stochastic non-parametric regression technique where the assumption is really that all evaluations of the function f are jointly Gaussian distributed. So if we were to evaluate our function f on a vector of inputs x1 to xn, this results in a joint Gaussian distribution parameterized by a mean function as well as a kernel function specifying the variance between the different function values. Now this encodes a distribution over functions which differs depending on the ingredients that we choose, that is the mean function and the kernel function. For example, many kernels are associated with a length scale, and if we have a very short length scale, that means that the functions that we consider are allowed to fluctuate very quickly with changes in the input, whereas if we have a long length scale, then we have very smooth functions that don't change a lot. Of course, learning is in the end done by collecting measurement data and then constructing the posterior distribution of these functions. And this can simply be done by Gaussian conditioning on the collected measurement points. However, this can also be expressed as a modification of the mean and kernel function, which is why we stick with this simple notation that we have here. The setup that we consider, therefore, consists of a dynamic system whose dynamics function f is drawn from such a Gaussian process, where we additionally assume that we have Gaussian IID disturbances acting on the system. Now we present the results for these autonomous systems, but they can be easily extended for the controlled case. We are interested in the distribution of a trajectory of such a system for n time steps ahead. So we want to know the distribution of states from x1 to xn. And if we simply plug in the definition of the Gaussian process that we had earlier, we can write down this implicit description of the distribution, where it is an implicit description because the states x1 to xn appear both on the left-hand side and in the description of the distribution itself. Additionally, matters are complicated by the fact that the system violates the Markov property. That is, the distribution of a state at a given time step does not only depend on the previous state, but on the entire history. This makes even simulation of the system or generating trajectory samples challenging. Many established methods therefore neglect this correlation, which then simplifies the simulation and also allows for the application of established direct approximation techniques of the resulting trajectory distribution. In our contribution, we look at different ways of explicitly addressing this correlation between different time steps. We discuss three different approaches. The first generates samples from the true trajectory distribution by employing a successive Cholesky factorization of this variance matrix. The second method we discuss considers approximate function samples and then simulates the system for these approximate function samples, which can have computational advantages. Lastly, we propose a modification of established direct approximation methods that allow to explicitly take this correlation between different time steps into account. Now finally, I want to illustrate some of the implications of neglecting this correlation between the different time steps by looking at two different distributions over possible dynamic functions, where the first one on the top has a very small length scale, so we consider quickly fluctuating functions, whereas the second one is very similar, but we have a long length scale, so we consider these very smooth functions. Now you can notice that for a single evaluation, actually these distributions are the same, so that if you neglect the correlation between the different time steps, you will actually not be able to differentiate these two cases. However, if we simulate these systems, for example with the techniques that we provide in the paper, then you can see, and this is demonstrated in the shaded red area, that the distribution over the trajectories actually varies significantly. This means that not differentiating between these two cases can have severe consequences, for example, in safety-critical control applications. And with this, I want to thank you for your attention, and for more information, please see our paper.